Now, if you follow the Huffman procedure on this on this set, what do we get? Well, let's list the letters 0 and 1 in decreasing order of probability. Combine them together. And done. So basically I assign a 0 to a 0 and a 1 to a 1. And my average encoding length is 1. So in other words, no compression has happened. Anyone suggest a way to improve on that? So what's the main problem here? The main problem here is that I only have two elements to work with. How do I increase the number of elements? What if we look at pairs? So if I have 0, 0, 0, 1, 1, 0, 1, 1, what's the probability of a 0, 0? It's 49 over 100. Probability of a 0, 1. 21 over 100. Same thing with 1, 0. And 1, 1. 9 over 100. So over here, if I draw a list of those, combine these two, and I get 1, 0, 1, 1. That is 21 over 100. The total probability of this event, 1, 0, 1, 1, is what? 21 plus 9 is 30, so that's 30 over 100. And this is still 49 over 100. Let's combine these two, and I get 1, 0, 1, 1, 0, 1, and 0, 0. So this is probably 49 over 100. And this super event has what probability? 51 over 100. And then I'm done. So let's assign this 0, 1, 0, 1, 0, 1. So to a source to code word. Okay, source letters 0, 0, I assign a 1. Source letters 0, 1, I assign 0, 1. Source letters 1, 0, I assign 0, 0, 0. And source letters 1, 1, I assign 0, 0, 1. So, now the average length is what? This is 1, 2, 3, and 3. So the overall average length is 1 times 49 over 100 plus 2 times 0, 1, probability of that is 21 over 100, plus 3 times the probability of this, which is 21 over 100, plus 3 times the probability of this, which is 9 over 100. Which is 0.49 plus 2 times 0.21 is 0.42 plus 3 times 1 over 100 is 0.63 plus 3 times 9 is 27, so that's 0.27. And I end up with, that is, these two together are 0.9, and these two together are 0.91. So taking those together, 1.81. So wait a minute, this is much worse. Pardon?
I was going to say that it's not possible, like if it's like number of days possible 0, 1 and you got 2 possible 0, 1, you can't get better than 1. I mean,
You got it. So we're sending 2 bits at a time, so this is 1.81 bits per 2 bits. So in fact, we've compressed to 0.905, which is better.
but
So what is your question? You can't.
no, my thing is like, yeah, I understand you're sending 2 bits and you're getting 1.81, but like we can already differentiate by just sending yeah, I guess, yeah.
Yeah, so I mean, basically what we're doing is we're taking each pair. I mean, at some level, these are just labels. So basically, I'm just taking labels and turning them into bits. So I could call this ABCD if I wanted to. Yes?
Is there a limit to this type of compression scheme?
No, in fact, so you go pairs, triples, quadruples, and so on, and as that goes to infinity, this should approach entropy. There's no, in general, more combination is more complex, but better as far as compression is concerned. Okay, any questions on that? So that's all we're going to say about compression, except one thing. So why don't we, Zip doesn't use this. Why doesn't Zip use this?
They can do a lot better. They do.
Actually, so the answer is no. This is actually the best thing you can possibly do. But what do you need to know in advance in order to do this?
Sequence.
You need to know the probabilities in advance. So Zip and related procedures use an algorithm called Lempel-Zip. And what Lempel-Zip does is it basically starts out not knowing anything about it. It's a so-called universal compression in which you don't need to know anything at all about the statistics of the underlying source. So another particular assumption that we use here is that every bit is independent, but that's not necessarily true in general. So Lempel-Zip is actually robust to that. It can still compress and get very, very close to entropy, even when the underlying source is not memoryless. And in fact, memoryless sources with memory are quite common. So, for example, an image. A memoryless source, if I had a pixel that was red, then all of the pixels surrounding it could be arbitrary colors. But we know that when we look at a picture, if a pixel is red, then the surrounding pixels are very likely to be red. So that's an example of a source with memory. And this procedure, we could make it more complicated to account for that, but in that case, we'd need to know all of the memory structure, which is very hard.
So
Yes?
if we're trying to differentiate between just two like values, then why would we send a pair and not just 0, 1? I guess my question is, if the probability of 0 was 0.5 and probability of 1 was 0.5, it would be better to just use 0 and 1 instead of a pair?
Okay, so that's an excellent question. So if we have this, what's the entropy of this source? So let me write it down.
Minus, no, it's